Okay, good morning, everyone. We come to lecture 3. So in the last 2 lectures, we have learned some electronic properties of graphene by calculating the Hamiltonian and the energy spectra. So we will continue to do more about graphene in this lecture. Let's review a little bit what we have learned. So we know that graphene has a Hamiltonian H bar VF, and then we can write it as tau kx sigma x plus ky sigma y. So for simplicity, we neglect the band gap opening term. So tau is the valley index. So sometimes for simplicity, you can just set it to be 1, but there's another value with a -1. Okay. So if you solve this Hamiltonian, you will find this Dirac-Cohn dispersion. Okay, so this is what we learned before, and this is in contrast with the conventional particle. So for conventional particle, you have the Hamiltonian, which is quite simple. You have a Hamiltonian like this, and then the dispersion is like that. Should be parabolic band. Okay, a parabolic band like this. Okay, a parabolic band like this, and you usually open a band gap, then you have another term. Okay. So these are the conventional particle. This is what we call the massless Dirac fermion in graphene. I mean, you can assume both of them are 2D system. For conventional system, like those quantum well, semiconductor quantum wells, or maybe in gallium arsenide, the dispersion are described by this conventional Hamiltonian with this quadratic relationship. So far, we only learned this in a kind of a theoretical way, okay? But in experiment, it's actually not easy to distinguish them. Okay, in experiment, you measure the absorption, or you measure the transport property. You don't actually see the Dirac-Cohn. You only see the signal, optical signal, electronic signal. You cannot see the Dirac-Cohn directly unless you do the RPES. Okay, so how do people distinguish these two kind of particles? Okay, how do you distinguish them, like from experimental point of view? So people use actually a method that is not. I mean, it's not it's not very conventional, but not very special either. That is, they study the property under the magnetic field to distinguish them. Okay, that is to study their Landau levels. So today we're going to calculate the Landau levels of these two kind of particles and see the difference and how they would give us a certain signature in quantum Hall effect to tell the difference between them. Okay, so let's deal with the conventional particle first and get the Landau level. And then after that, we'll get the Landau level of the Dirac fermion. Then we will see the difference. Okay, we'll see the difference. Okay, so let's go with the conventional particle. So let's consider a free massive particle. In a uniform magnetic field. Yeah. So basically, is an electron, and then you have a 2D plane, and then you apply the B field. The B field is equal to B z direction. Okay, z direction. I mean, you can define the XY plane as well. So what is the Hamiltonian? The Hamiltonian in this system, we use something called the minimal coupling or minimal substitution. That is, initially you have a p square. This should be a vector. So the minimum substitution is that you substitute p with p minus qa. So this is called minimal people, you can call it minimum coupling or minimum or minimal substitution. So that's a kind of a recipe when we deal with the particles coupled to the EM wave. So this A contains the information of the field. Okay, so in this Q, Q is the charge of the particle. Okay, so then this will become HP minus Q A squared 2M. Okay. For electron, Q equal to negative E. E is positive here. Okay. E is the fundamental charge. That is the charge of the proton. So we make it positive here. Okay, we make it positive here. So this is an exactly solvable Hamiltonian. So let's solve it. Okay. So we'll use let's consider the Landau gauge. Okay, Landau gauge. So A, I mean we are going to try this Landau gauge 0, Bx and 0. Okay, so you only have the y component here. You only have the y component here. So from this, you can already get this result that you get a curl of A, you will have BZ. You can easily verify. Let's just quickly verify it. So you know the definition of curl is that you have the I component equal to I, J, K, J, and K. So if you get the X component, then you have this this will be dy az minus dz ay, and you don't, the z component is 0, so this term is 0. The y component is bx, but there's no z dependence, so it's 0. Okay, if you consider the y component, then you have the dzax minus dx az, and the a and z component are all 0. So it's also 0. If you consider the z component, so you have the dxay minus dyax. So the y component here is bx. The x component is 0, so you have b. So you get the z component to be b. So you verify this. Okay. Another choice is you can also use negative by. And you do the same thing, you get exactly the same result. Either way is fine. Either way is fine. Some people use this choice. Some people use this choice. And eventually, you get the same result. You get the same. Why do you have a negative here? Because this z component, once you do the derivative on y, you have a negative sign here. Okay, so this one take care of this negative sign to give you a b. You can verify by yourself. Okay, so okay, so now let's get the Hamiltonian. Okay, the Hamiltonian is 2mp negative qa. So here we're using the SI unit. We're using the SI unit. If you use the Gaussian unit, all you need to do is to add over c in the bottom. So this is the Gaussian unit, and this one is the SI unit. Okay, so only a factor of 1 over c difference. Okay, so I take this. Then we change it to the electron because the charge is negative e. Okay, the charge is negative e. And then we open it. Okay. And then plus e p dot a plus e a dot p. Okay, so we can make this px plus py plus pz. Okay, I mean these are all operators. They're operators. And this one, a square is just this bx. Okay, it's just bx. So this is just b square x square. Okay. So and you just use this copy. So basically, this one just equal to a y. You only have the y component here. You only have the y component. So here, this will be the py. The dot product only take the y component, and then you have the bx, and then plus e bx py. Okay, py. So py and x they commute with each other. So py x they commute. So these two you can let me rewrite it. Copy. So you can just add the 2 here, add a factor of 2. Okay, they commute. Okay, then you can observe that this py, I mean this px, and this one, you can combine them together to give you a new term. Let me just write them separately. You have a px 2m plus 1 over 2m. Then you can have a EB, sorry, EBX and plus PY square. And then plus PZ square 2M. Okay, so you just combine combine this, then you get this. Okay. Okay, then now let's bring out this EB. Okay, if you bring out the EB, then they become square. So you have X plus PY BE square. Okay, so here, let me copy this. Here you can add the M here. You can add the M here. Then this will become M square. Okay. Then you could change it into 1 over 2 M and then EBM squared. Okay. EBM squared. So we define this as omega, let's say omega B then. As the cyclotron frequency. Okay, cyclotron frequency. This one can be neglected in 2D system. Even in 3D, this term is just it represents the free motion in the z direction, so it's not significant, not very relevant in our comparison here. Okay, so you can neglect this term in the 2D systems. Even in 3D, you just add the plane wave in the z direction, then you take care of this term. So let's make it simple and we neglect this term. Okay, so you'll find that the Hamiltonian has this form, and 2m omega b square x plus py be square. So let's try a trial wave function. You need to know that here h commute with py. So py is a good quantum number. Is a good quantum number. Okay. So what is the eigenfunction of py? It's just a plane wave. Okay, so you can separate that plane wave out. Then the wave function will become EIKY y, and then you have the x part. You put it here. Okay, so you and once you try that, then it will be px, and then so the py will become this one will become h bar k, will become h bar k, ky, and b square. So after you apply that, then is this ky is just a number. It's just a quantity. It is no longer an operator. Okay. Okay. So you can set x0 as negative. You can set this. Then this equation will become, copy, will become this. Okay, will become this. So here, you can see that this is an operator, p is an operator, x is an operator, and all the others are just numbers. Okay, and this is the form of a simple harmonic oscillator. Simple. So I mean, in quantum mechanics, we have learned how to solve the Hamiltonian of a simple harmonic oscillator, and this is the equation for that. Okay, and we already know the energy will be n plus 1/2, and n equal to 0, 1, 2, 3. Okay, and here this omega b is the cyclotron is the EB over n. Okay, so that's it for the conventional massive particle. So probably you already learned this before, how to solve the Hamiltonian of a free particle, massive particle under electric field, under magnetic field. Okay, is it okay? Any questions? Okay, now let's go to solve the Hamiltonian of a massive Dirac fermion under magnetic field. So now let's consider this Hamiltonian. Copy. Okay, so fermions under uniform magnetic field. So let's consider just one valley then. Let's consider tau plus 1. So just make it simple. And then H will be VF, and then H bar V, H bar KX plus H bar KY, and this will become PX, PY. So now, under this substitution, So it will be plus E for electron. Q equal to negative E for an electron. Okay. So this will become Px plus EAX plus Py plus EAY sigma Y. Let me move this. Okay. So let's write it out. Let's write it out. This will be 0 Px plus let's simplify first. So let's go to get the Landau gauge. Copy. Okay, we use the Landau gauge, then the Hamiltonian will be P. Here the AX is 0. Okay, so you only have PX sigma X, and but you still have the Y component. You still have the Y component. Okay, you still have the Y component. Then you just write it out. You just write it out. So this will be Px and then minus I and then Px plus I EBX X. Okay, EBX. Then let's consider this function has two components, 1 and 2, and the Hamiltonian of this equal to this. Okay, so we're going to solve it. Then you have 1, 2, and then you have energy. Okay, so let's just make this operation here, this matrix on this wave function, a set of two wave functions. Then you will have VF Px minus I Py EBX psi 2 equal to E psi 1. And then you also have VF Px plus I Py EBX. Okay, you have a set of these two equations. Then we're going to solve it. It's actually not very difficult. So from the first equation, you can already get let me see. You just move this. You just move this here. Okay, this is 1. This is 2. from 1. Okay. So put it into 2. If you put it into 2, then copy. So you just put this whole thing into 2. Copy. Okay. Put it into 2. Then you have this equal parts. Okay, let me take some space. Yeah. Okay, then you get this equation. You get this equation. Let me see. Okay, so we can move. You can slightly make it better. Like copy this. Copy this. And then on the other side, you have the E square over velocity square by 2. Okay, so let's open this parenthesis. You open it. Let's just open all of the terms. Let's open all of the terms. If you open this, you get IPY plus I. So here you get negative IPY. You get negative I. Okay, so you open it. How many terms you have? You have 9 terms. Px squared. Let's just deal with that one by one then. And then negative I EB PXX plus I PY PX. This one and this one, you get PY square. And then this one and this one, you get PY EBX. And then you just continue. I EBX PY. And then plus EBX PY. This term and this term. And then plus EBX and EBX. Okay, so you get all of this. So I'll do it like this. Okay, here you have some cancellation here already. So this term cancel with this term. Let me see, any other cancellation? Okay, and then let me see. This term and this term. Okay, so let's consider these 2 terms. Okay, so this 2 term will be negative I EBPXX plus I EBX Let me see. Did I make a mistake anywhere? Ah, okay, sorry. This is X. Yeah, this is X. This term times this term. Okay, this is Px. Okay, so this is Px. So if you take IBE out, then it will be X minus PXX. Then this is just the canonical commutation. So this one will be IH bar. So this whole thing will be negative EBH bar. Okay, negative EBH bar. And these two terms, they're the same. They're the same. Because X and PY, because X and PY, they commute with each other. So these two terms are the same. Okay, so after that, we can get a Hamiltonian like this, the equation like this, plus this, plus 2 EBXPY plus E square B square X square and minus EBH bar. Okay, so this will be phi 2 E square VF phi 2. Okay, so let's continue. And then this will be we still have the PY. Okay, we missed the PY. There's a PY here. Okay, there's a PY. Then this can combine. You have the EBX plus PY square. Now PY and X they commute. Okay, so you can have the EB out square X minus PY EB square. Okay, so you can write it as this plus E square B square and then phi 2. So you can move this term. This is a constant. So you can move it to the other side. Okay. Okay, now let's compare. Let's compare. Let's compare it to the equation of the massive particle. So we get the equation of the massive particle in the previous section. Yeah, this one. This one is the equation for the massive particle. By the way, here you can already set. You can, because here you have the py that is kind of a it is commute with this, so you can try p2 with the e iky times y, and you can try this. Okay, so with this, then this equation will become, then this one will become h bar ky, and you have this. Okay, you have this. So you can set this equal to negative ky eb. This is what we have done before. And then this one will be negative 8. Okay, so you have something like a simple harmonic oscillator on one side. Okay, so if you compare this with this, so here omega b, what is omega b here? If you check omega b, omega b is yeah, this one. This is omega b. Copy. So this is omega b. So if you put omega b inside, this will be e square b square m square. We're kind of doing it backward. Okay, so this whole thing will become let me see, what is that? 1/2 e square b square m. Okay. And then you just move the 2m to the other side. You move the 2m to the other side. So here E equal to h bar omega b m plus 1/2. Okay, so what is h bar omega? This one is EBM. Okay, EBM. So consider, so this equation will become will become 2m with this thing. Okay, so then this m will cancel. This m will cancel. Okay, this m will cancel. So eventually you only have the 2h bar EB. You only have 2h bar EB. Okay, so we get this equation. For massive particle. Okay, let's compare this one. Copy. For for massless direct fermion. Massive, you can say this is conventional. Conventional means that it is described by the Schrodinger equation. So you see that they have the same form. Okay, you just compare. Okay, yeah, px e squared b squared e squared b squared. Okay, this term are the same. And this is a constant. These are the energy term. This is also a constant term. Okay, so by comparison, you already know that the solution of this equation just follows straightforwardly from this equation. Okay, so from the comparison, we get, what do we get? We get this thing. Yeah, we get this thing, copy. Equal to this. Okay. Equal to this. So what is E? Then E equal to 2h bar EB n plus 1/2 minus EBH and VF square. Okay, so here you can open it. You can open it. You have 2h bar EBN plus h bar EB minus this here is EBH bar. So you can already see that these two terms will cancel each other, and this is a significant result. This is a significant result because the Landau level will be quite different. Okay. So basically, this is EF squared times 2H EBN. And then the energy will be square root VF 2H EBN. Okay, here n is 0, 1, 2, 3, ... This comes from the massive equation, because in this equation, n equal to 0, 1, 2, 3. That is the solution of this equation, and you get the equation with essentially the same form. But instead of just an energy here you have an energy square over VF square plus a constant term. Okay. So there's another way to write it. That is, we allow n to take a negative value. If we allow n equal to 0 plus and minus 1 plus and minus 2 plus and minus 3, then we can make it like this: the sign of n and then VF 2H EB and absolute value. Okay, so this is usually the equation that you see in the literature. Okay, so n equal to 1, 2, 3 corresponds to the electron to the electron side. And n equal to -1, -2, -3 corresponds to the whole side. And there is the n equal to 0 level at the n equal to 0 at n equal to 0. So this one, you cannot say it is on the electron side entirely. You cannot say it is on the whole side entirely. It's in the middle at the direct point. Okay. So you have this thing. You have this because you have a cancellation here. Okay. You know that this one comes from this 1/2, right? You have a 1/2 0 like ground state level. Even when n equal to 0 in conventional state, you still have a finite energy. But here, you have this constant term that cancel out this. So actually, this move the Landau level down to 0. Okay, so that is something significant. Okay, significant. So you have a 0 level. Okay, so basically that is the result. That is the result. So let's compare the Landau levels. Okay. Conventional massive particle. So you have okay. Let's draw the. Let's draw this one, something like that. So the Landau level will be you have a Landau level in, and this is n equal to 0, and then they're all evenly spaced. They're all evenly spaced. N equal to 1, and yeah. So these are the conventional ones. But for Dirac fermion, is not the same. For Dirac fermion, so first you have a Landau level in the middle. Right. You have n equal to 0. This is one level. Then here you can see that the spacing is equal. The spacing is equal, evenly spaced. But here is not evenly spaced. Let's just write the energy level. The energy level is equal to, and here the energy is like this. Copy. So you have an energy that is proportional to n square root. Okay, that means when n is when n is different, the spacing is also different. Okay, it's also different. So it turned out that you have a level like this. You have a bigger spacing, and then a smaller spacing, and then even a smaller spacing. You have something like that. Okay. -1, -2, -3, ... Unevenly spaced. The spacing between levels drops when n increases. When n increases. So the scaling is different from these two cases. Okay, so this is one difference. Another one, of course, here, yeah, no level at e equal to 0, and there is a level at e equal to 0. Okay, so this is another difference. And there's also another qualitative difference. That is the energy gap are very different. Okay, so let's consider the energy gap. Like so here the energy gap is just h bar times the frequency. So for example, let's consider non-relativistic electron at B equal to 20 Tesla. Okay, so this one will be h bar. Okay, EBM. So you just plug in the number. So h bar is 10 to the negative 34 joule second, and then an electron. An electron, you just put the mass of free electron, and then you just put in 20 Tesla. This is the charge, not mass. Sorry. Okay, so this is the mass of an electron. We're using free electron. So in a normal like solid, the effective mass will be smaller than that. Okay, will be smaller than that. Okay, then you get a value that is about this. This is about 2.5 millieV, approximately 30 Kelvin. Approximately thermal energy at about 30 Kelvin. Of course, it really depends because the effective mass, it really depends on the solid. Okay, but for MOS2, for example, then it's about 1/2 of the effective mass. So it's not too different from that. But for this direct fermion, there's no mass. Okay, there's no mass. So let's make it smaller. Okay, so for the massless. Okay, the spacing here, the energy gap, the largest energy gap between n0 and 1 equal to VF to H bar EB. Then you put in the number. This is 10 to the 6 meter per second. And then here you just plug in the number h bar times 1.6 10 to the negative 19. And then you also have the charge. I use the charge first. This is the charge. So times. Anyway, I should put this first. This is the charge. This is h bar. Okay. And then 20 Tesla. So this is about 2.5 10 to the negative 20 joule. So it's about 160 milli EV. So this is so you can see that the energy spacing is very large. It's very large. Okay. Much larger than this. So much larger. Of course, if you have a system with a very small effective mass, then you can make the this higher. So if the effective mass equal to, let's say, 1/2 of the electron mass, then this is an inverse relationship, right? Then the energy gap will become 25 milli EV. Then it will be thermal energy at T about room temperature. Okay. So this is a relatively small effective mass. But even with that, you only get about 25 milli EV. Okay. But if you say for some of those material, the effective mass is 0.2, 0.3. So relatively, it's still somewhat like a relatively low temperature. But if you compare this one, it is a much higher, significantly higher. So that means in graphene, it's much easier to see to observe the Landau level because the spacing is big. Okay, so that is one key feature. So actually, people can observe the quantum Hall effect in graphene even at room temperature. I mean, this is one factor. Of course, they need to apply a very high magnetic field. But this is one significant factor because the spacing is big. Okay, but of course, another reason is because the suppression of the scattering and the sample quality is also good. All those things combined together. But this energy spacing is some intrinsic property of the linear dispersion. Okay. Okay. Any questions?
If you reduce the effectiveness more, then can it exceed this?
Mathematically, yes. Yeah. I don't know. Yeah. If you make it 0.01, then you have another factor. You have another factor of 10. Yeah.
I'm just curious that if that effectiveness is so small, then it can rather not valid on relativity.
I mean, this relativistic or non-relativistic, basically, it means whether it is, I mean, if it is all described by the p square over 2m Hamiltonian, is always not relativistic. So I mean, the effective mass is somewhat related to the band gap size. If your band gap is big, you will have a certain curvature, and you have the mass there. So if you say you want to decrease the mass, you're basically saying that you want to decrease the band gap. Okay, if you decrease the band gap eventually to 0, then you have a direct cone. So you're kind of always approaching the massless case. So I mean, you know what the mass is, right? The mass is the inverse of this curvature here, right? So if you want the mass to be small, then you have to make it like this. Then eventually they will approach, and eventually you have a direct cone. Now, once the band gap drop to 0, then you get a cone. Okay, so you can drop this mass, but you're just approaching the massless case, like according to this picture.
So can I think that if we think about the extreme case, that the mass is small, then in the case of the direct cone?
Yeah, when you go to massless, then you have a cone. But because, of course, when we consider the massive case here, we only consider one part. We did not consider the valence band. So we only consider this part. Yeah, so when you consider this, then it's relatively simple. But once you go, the band gap becomes smaller, then I think the description will be more correct if you consider the two bands together. Then you eventually once you have this cone, then you describe it is the Dirac fermion. Yeah, I think it is the case, right? Once you have a cone, then you go back to the Dirac fermion. Okay, so let's consider why there's such a difference in the spacing. Okay, so first, let's consider the degeneracy of the Landau level. Okay, the degeneracy of the Landau level. Degeneracy of Landau level. So for the conventional case, so let's go to a conventional case. What determines the degeneracy? Okay, in this case, in the conventional case, okay, this is the conventional case. So you solve it, you have one level, but this level does not depend on this x0. X0 here is a parameter. That means when you have a different x0, you have a different level. Okay, yeah, basically, after you solve it, you have a wave function in terms of x, but this x is related to the x0. If you shift the x0, you have another wave function. So how many levels are in this Landau level depend on how many x0. Okay, so let me see. So let me just copy this. Okay, let me copy this. The degeneracy is the number of allowed x0. That is the number of allowed ky. The number of, let's say you have your sample have a certain size. The sample have a certain size. Let's say your sample size is this big. Okay, so you know this ky is basically how many kind of a standing wave or periodic wave function you can have in this spacing. Okay, like Ly. Okay. So when you fix the Ly, then the number of allowed Ky will depend on this Ly. That means the larger the Ly, the larger the Ly, the more allowed Ky we have. Okay. But since your sample is fixed, so the degeneracy is always a constant for both the conventional and direct fermion case. Is always a constant. I think this probably is more useful than remembering the formula for the degeneracy. The degeneracy. Okay. Basically, for each cyclotron motion, you have a certain radius. Okay. If you draw in different way for each cyclotron motion, basically you have a simple harmonic oscillation center on x0. That this x0 is drifting. Okay, it's moving with different ky. So basically, you have different cyclotron motion, and the bigger the sample you have, then of course you have more this kind of cyclotron motion. Then you just count how big your sample is. You just count how many of this cyclotron motion you have. Then that is the degeneracy. Okay, it's always a fixed number because your sample is fixed. Okay. So the direct fermion case has exactly the same degeneracy. Why? Because you solve the equation by comparing the two cases. Let me see. Okay, you compare the conventional case with the direct fermion case, and then you solve it for the energy level, right? So this two equation has the same form, the same number of allowed x0. Okay, you have the same number of allowed 0. So the two set of system, they have exactly the same degeneracy. Is it okay? Because they have the same number of allowed x0, and this x0 just come from the y part. The y part is just a plane wave. So you have basically the same kind of consideration for the y part and for the degeneracy. And the number of states will not increase or decrease when you apply the magnetic field. Okay, like so it's just a redistribution. So for conventional case, do you know the density of state for the conventional massive particle? If you have a quadratic dispersion, okay, so the density of states, you plot density of states. You plot density of state as a function of energy. Can someone tell me what the density of state is? It's just a constant. Okay, it's just a constant. For 2D massive particle. Okay. It's just a constant. So when you have a constant and redistribute it into different Landau level, and each Landau level have the same degeneracy, then what is the energy spacing? The energy spacing will certainly be just constant. Once you have the B field, then the Landau level is a spacing. You always have a even spacing. Because each Landau level accommodate the same number of states. So do you understand why they're evenly spacing? Because the density of state is a constant, and each Landau level take the same number of states. So when you redistribute the density of states into the Landau level, then the energy spacing must be even. Okay. However, for Dirac fermion, the density of state is not even. I mean, you can clearly tell that this one has a bigger radius. This one have a smaller radius. So from the size of this ring, you can already know the number of states, right? So the number of states, or you can say the density of state is proportional to K in this case. Because it's the size of this ring. And the size of this ring is just K, the radius, times 2 pi. Okay? Times 2 pi. And what is K? Energy equal to H bar VFK, right? Okay? So that means the density of state is proportional to E, linear. Okay? So you will have the density of state, which is like this. Okay, you have the density of state like this. Okay, so the density of state is like this. Okay, so now each Landau level take the same number of states. Okay, so you have a Landau level here. Then let's say all of this go to here. Then you have another Landau level. Then you will take, let's say, this much. Then you have another Landau level. Because now you have more and more states, right? You have more and more states, so the spacing will certainly become smaller. Okay, if you have another one, let's say this one. Yeah, I mean, my drawing is not very good, so I hope you get the idea. So because the density of state is small in low energy, you need to have more energy to produce the same number of states to go to that Landau level. Once you go high in energy, then your density of state is larger. You need a smaller energy spacing to contribute to one Landau level. When you go to higher, then you need a smaller energy spacing. That's why the energy spacing drops when you go to higher energy. Okay, so that uneven spacing of the Landau level are entirely due to the uneven density of state. Okay, and for the massive case is even. The density of state is even, so you just take equal part. You just take equal part to go to each Landau level. Okay, is it okay? So this kind of Landau level has been observed. Let me show you this paper. Okay, so this is the Landau level that people measure in graphene. So you go to this paper, observing the quantization of zero mass carriers in graphene. This paper was in Science. Okay, so I mean, This is the spacing of the Landau level that they draw. Okay, you have the uneven spacing. I mean, there should be the one in the middle. Okay. Okay, there should be one in the middle. Okay, so this is the, I think this is the STM data, the STM data. So at zero energy, zero bias here, you have one Landau level. Okay, I mean, you can neglect these details. Okay, you have one Landau level. And then in high energy, you have another Landau level. And then you have a n equal to 2. N equal to 2. You can see that the spacing is big here. Becomes smaller, 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 smaller. So this is the spacing. Okay. So this is what people observe. Okay. And you can see how the Landau levels are formed. 0 Tesla, 1 Tesla. You can see that this lower n case always appear first. So because the spacing is big. And here the spacing is small, so they can easily merge together. Okay, you can see that they resolve the 0 Landau level first. Okay, and go. Of course, this one is also easily discerned. Okay. Okay, so this is the Landau level, uneven spacing. Okay, so now let's talk about the quantum Hall effect. The first unambiguous evidence of the Dirac fermion in graphene, I would say is you have many like a different way to probe it, but I think the most distinguished and unambiguous signature is in the quantum Hall effect. So let's briefly talk about the quantum Hall effect. So basically, when you have some Landau level, okay, let's consider some Landau level. Okay. Some Landau level. The quantum Hall effect is okay. Quantum Hall effect. So basically, you apply a voltage, and then the carrier. Of course, you need a magnetic field here in the conventional case. So some of the carriers will drift in one side. Will drift in one side. So you have the electron accumulated on one side, and then the positive charge on another side. And then you have the voltage, the Hall voltage. So generally, you will have two kinds of transport direction. One is along the XX direction. One is along the XY direction. Okay, one is along the XY direction. Then you can plot something called a. Let me see what they plotting here is XY. Okay. If you plot let's say if you plot the XX direction, okay, XX is the transport along the X direction, and this is Y direction. If you plot the conductivity along the X direction as a function of carrier density, then once your carrier density is in the middle, you have a half field band. So it will be non-zero. It will be non-zero. Okay. Let me okay. Let me consider the conventional case first. Okay, let's say this is E equal to 0. So you start to fill the level because you have an energy gap between 0 and 1. So there's some defect state here. You need to fill the defect state first. So when you fill the defect state, the energy here is, use a different color. Then you have zero, near zero conductivity because you are between the gap. So once you reach here, then you are in a half field. You are in a half field state. So you will go up. Okay. And of course, quickly you go to here again. Then you drop to zero. Then you go to another level. Then you go up. And then we drop to zero. Okay. Yeah, you have something like that. Okay. Yeah, you have something like that. Okay. So you are in you're inside the Landau level. Okay. Landau level. But once you're in the gap, there's the bulk of the material become insulating, but there's an edge state. Okay, the edge state will give you the conductivity. I mean, we need more lecture to if we want to study this phenomena. We need more time, more lecture to talk about it. But once you're inside the gap, the edge of the material will become conducting. And because the quantum Hall state is a topological state, when the bulk is insulating, the edge actually is conducting. So once you're in the gap, the edge will be conducting and it will contribute to this XY conductivity. And it will become you see a plateau. Okay. So when it is let me see, when it is in the gap, okay, when it is in the gap, let me see, it will be, when it is in the gap, it will be a plateau. Okay, it will be a plateau. Where should I put the plateau? So it will be a plateau here. Okay. And then when it is inside the Landau level, it will increase. And then another plateau. And then we will increase again. And then another plateau. And then we increase again. Then another plateau. Okay, so this step they're even because inside the gap you just increase the same number of edge states. Okay, so you have the XYZ showing a plateau step. I mean, these are the signatures of quantum Hall effect. Okay. Okay, now let's consider the Dirac fermion. Let's consider Dirac fermion. The Dirac fermion is this. Okay. Then you have a Landau level here. You have another Landau level here. You have another Landau level here. Okay. So what makes the difference is that the beginning point are different. Here, you're beginning from a gap. You're not in the Landau level. But here, once you inject carrier, you're already inside a Landau level. Okay, so that means if you plot because when you fill the carrier, the carrier cannot tell you the energy. Okay, you just get there and fill the particle. So here, sigma xx at the beginning is already inside Landau level, so it will be conducting. So you will be somewhere here. Okay, you're already inside Landau level. Then you are in the gap. Then it becomes zero. Then when you're in another Landau level, then it show up again. And then it show up again. Okay. Of course, you also see on the whole side, And then this sigma xy, once you are inside the Landau level, then you're increasing and you're increasing. Then once you are off the Landau level, when you are in the gap, then you see a plateau. You see a plateau. And then you increase again. Then you see a plateau. You increase again, then you see a plateau. Let me see. I should actually drop it a little bit. Let me draw it again. Let me draw it again. You should, because here is okay. So the key feature here is this. The key feature here is this. So the key feature here, you have a half a step. And here you have one step. Okay. So you can already see the patterns are different. This is one step. Another one. Okay, if you compare, the main difference here is that at the beginning, you're already on the plateau. Then you take one step, you have another step, you have another step. Okay, but for the Dirac fermion, you start in the middle of your step. You take half a step, you go to a plateau, and then you have another one. You have another one. So conventionally, people call this a integer quantum Hall effect, mainly because you just have 1, 2, 3, something like that. But here you can, if you use exactly the same convention, then the plateau will be in half integer. Plateau. The plateaus at integer positions. Here, the plateau will be in half integer. Okay, so you'll be in half integers. So some people call it some people call it half integer quantum Hall effect. Half integer doesn't mean it is a fractional quantum Hall effect. It's still integer quantum Hall effect, but because of the special position of this 0 level, Landau level, there's a shift for half a step. So the plateau begins at different position. Okay. So this is the main difference of the Landau levels between conventional massive particle and massless Dirac fermions. And you can see this easily from the quantum Hall effect. Okay, so historically, that was the signature that people they know clearly that it is the massless Dirac fermion, and it was reported in 2 papers. The first paper, they're backed by Back in Nature in 2005. The first one was by Novoselov and Guy, and these two got the Nobel Prize. So these are these are the data. Okay. So they plot the this green line. Let me see. This green line is this. Okay, this, and then let me see. And then this red line, the plateau. So you can see that the plateau was in the middle. Okay, was in the middle. You have half a step, and then you have another step. You have another step. Okay. Then this one is from Philip Kim's group. It was also in Nature. So then here they plotted. They plot in somewhat in a different way. They're using the resistance. But here they plotted in a somewhat different way, but you can still see the step occurs at 0. Okay, and these are the Landau levels. Okay, if you're interested, you can read these 2 papers. I mean, this is the energy relationship that we obtained in this lecture. They also have it here. Okay, do you have any questions? Any questions? Okay, so basically in today's lecture, we just talk about the Landau levels of these 2 different cases and the signature in quantum Hall effect. Yeah. Okay. And in MOS2, I mean, we didn't talk about MOS2 today. In MOS2, it is the particles are massive, but it is a direct fermion, so it will be somewhat different. In MOS2, you will have a gap, but the Landau level will actually start from 0. Yeah. In MOS2 is massive direct fermion. I mean, if you're interested, you can solve the Hamiltonian, add the massive term there, and see whether you can get this kind of Landau level. So it actually starts from 0, and then you have because it is massive, the energy spacing will be somewhat different. But there's one value that will start with 0. Okay. And the other one will be somewhat different. Let me see. We have let me quickly go to the paper. Sorry, I didn't open the paper. Why there's no response? Let me see. This one. Okay, so here we plot the Landau level of MOS2. Okay. So there are 2 values, K and K prime. So in one of the value here, you have a Landau level at 0. Okay. I mean, that is what is due to that canceling term. Okay. And then the valence band, you start from -1. Okay. But on the other value, that 0 Landau level goes to the valence band. Okay. and then this start from 1. So I think you can obtain something like that if you go back to revisit the Hamiltonian. You add the massive term, add the valley index, and you just solve the Hamiltonian. I think you would get something like that. I mean, we didn't do this today, but I mean, you can see how I solved the Hamiltonian today, right? So if you add the valley index, add the band gap there, and you solve it again, I think you should get something like that. We didn't do it today, but you know the underlying principle. Okay, so it's not exactly the same as the conventional massive particle, and not the same as the massless case, but that direct form of the Hamiltonian, that matrix form, will make the difference. Okay, so this is the case for the massive Dirac fermion. Okay, and of course, one of the novelty in this paper is that we somehow detect this zero energy level. Okay, so in our data we actually resolve it. We can see the zero case. Okay, and we also see the plus zero, but of course this is on the other side. We see the plus zero, and when we dope it on the whole side, we see the negative zero.
Data says it's the same value.
Let me see. The same valley, but the valley is the one that we probe the optical transition. We're probing the optical transition in valley, but when we dope it, the doping goes to another valley. Like you're doping different valley, but we're probing the optical transition in the same valley. So anyway, we didn't talk about this at details. So MOS2 is somewhat related to graphene, but not exactly the same. You add the massive term, and you solve, you should be able to get it. Okay, any other questions?